Hey everyone, welcome to the last video for section 3.7. So in this video, we're going to do a little discussion about LRC circuits and how they actually end up solving the same equation so we already know how to solve them. And then work through a couple examples of the types of problems that might show up out of stuff like this. Now, problems like this are kind of tricky because they're hard to do without some sort of computer to help you. But we'll set out some problems and see what they look like and see how you can sort of still work things out in some of the easier cases. Let's go ahead and jump on into it. So the first thing we want to look at is electrical circuits. So let me draw a little circuit picture, which I'm sure all of you are familiar with, especially those of you who are taking the electronics class and stuff right now. I've probably seen way too many of these, but we got to talk a little bit about them at least to show you how this all works. So let's take a look at this and look at voltage drops around the circuit. So the resistor, what's the voltage drop? Well, the voltage drop is I times R, or if you want to write this in terms of charge, it's dq dt times R, where R is the resistance of the resistor. If we look at across the capacitor, the voltage drop is Q over C. And if we look at the inductor, the voltage drop is L times di dt, which is L times the second derivative of Q dt, because current is the derivative of charge. And now we have the battery or the source, which is going to be some f of t that it could be constant, it could be an AC circuit, anything like that. It's given there. Then what does Kirchhoff's laws tell us? Well, the Kirchhoff's laws tells us that the voltage drop around the whole thing has to be zero, which means that the source has to be the same as all the other components. So Kirchhoff's laws tells us what? They tell us that this f of t, or the source, has to be equal to the drop across the inductor plus the drop across the resistor plus the drop across the capacitor. And what do we have? We now have a second order linear constant coefficient ODE for Q. So it's second order, it's constant coefficient, it's linear. So we're back in the exact same case we were before for mass on a spring. So if you can solve the mass on a spring problems, you can solve these problems. You just have to know how to translate the problems into the word problems into math to be able to do it. Besides that, they're the exact same problem. All right, so with that out of the way, let's go look at some examples. I'm going to write them in terms of masses on springs, but you can write them in terms of inductors or in terms of circuits. It doesn't matter. They are effectively the same problem. So let's take a look at an example here. All right, so here's an example problem. I wrote it up because it's a lot of words and didn't want to write that while I was talking about it. So we have a 2 kilogram mass that hangs from a spring with spring constant 4 newtons per meter and resistive constant 4 kilograms per second. We want to know if this is underdamped, critically damped, or overdamped, and we want to solve the problem with the initial condition that the mass is pulled down 2 meters and released. So let's start with step 1. What is our ODE that comes from the system? Well, the ODE we know we want is mu double prime plus gamma u prime plus ku equals 0. Here m is 2, k is 4, and gamma is 4. So here's m, here's k, and here's gamma, just from how the problem is stated. So I have 2u double prime plus 4u prime plus 4u equals 0. And now I want to get to a characteristic equation and solve for the roots. So my characteristic equation is going to be 2r squared plus 4r plus 4 equals 0. And can quadratic formula this right away. I get r is negative 4 plus or minus the square root of 16 minus 4 times 2 over 4 is negative 4 plus or minus the square root of minus 16 over 4. If you simplify that out, you get negative 1 plus or minus I, because the negative 4 and 4 will give you minus negative 1, and then the root negative 16 is 4I. So my roots are negative 1 plus or minus I. So this can tell you right now, what does this mean? Am I overdamped, underdamped, or critically damped? Because I'm going to see oscillation, this means I am underdamped. And then we want to solve the problem. So if our roots are negative 1 plus or minus I, that means our general solution is u of t equals a e to the minus t cosine of t plus b e to the minus t sine of t. Okay, So now what I want to do is plug in my initial condition. What was my initial condition? I said I was pulling it down 2 meters and then releasing it. So what that means is my initial condition is u of 0 equals 2. Remember, because down is positive here. And u prime of 0 equals 0 because I'm releasing it. Right? I'm releasing it, which means it's just going to go up at that rate. I'm not throwing it any direction or other. I'm just letting it go. So its initial velocity is going to be 0. So let's plug this in. So u of 0 being 2, u of 0 is a plus 0 because the sign of 0 is 0. So it means a is 2. And now let's look at what u prime of t is. U prime of t with a being 2 is going to be a minus 2 e to the minus t cosine of t minus 2 e to the minus t sine of t minus b e to the minus t sine of t plus a b e to the minus t cosine of t. And now I want to plug in t equals 0, which means all of my sine terms are going to vanish. So u prime of 0 is just a minus 2 from this first term plus a b from the last term. So this tells me that b is also, and I want this to be 0, which tells me b is also 2. So a is 2, b is 2. My solution is this. U of t is 2 e to the minus t cosine of t plus 2 e to the minus t sine of t. And there's the answer to my problem. I saw that it was an underdamped solution, which means I should get oscillations, and I have oscillations at the answer. So there is that example of a problem. Let's take a look at a second one now, which is going to be a little different in nature, but a similar idea. All right, so here's this example. In this case, I want you to find the gamma so that this ODE, u double prime plus gamma u prime plus 8u equals 0, is critically damped. Solve the equation with that gamma for u of 0 equals 2, u prime of 0 equals minus 5. So in that case, I've cut the word problem stuff out of it. I've just written the problem directly as it is. But this could be phrased in terms of a word problem, and you'd have to be able to interpret it in this form to be able to solve it from there. So let's start. How do we start? We're looking for critically damped. So let's do this via the characteristic equation. So what is the characteristic equation here? Well, this is going to be r squared plus gamma r plus 8 equals 0. And we can go to the quadratic formula and look at that r is going to be negative gamma plus or minus the square root of gamma squared minus 4 times 8 times 1 over 2. And now, what do I want to be critically damped? I want this part of the square root to be 0. So for critically damped, I want gamma squared equals 32, which is 4 times 8, or gamma equals 4 roots of 2. So there's the gamma I want for this problem. Now I want to solve my equation using that gamma. What do I know about my general solution in this case? Well, if this part of the square root is 0, my r is just negative gamma over 2, and it's a repeated root. So that means my general solution, u of t, is going to be a plus bt times e to the negative gamma t over 2. Or if I want to plug in what gamma is, I get a plus bt times e to the 2 root 2 times t, with a negative sign in front because there's a negative sign there. So now I want to solve using our initial conditions. So u of 0, which I want to be 2, is what it's just going to be a, because b times 0 here is going to vanish, and this is just going to go to 1. So a is 2. And I want to take the derivative. So what is u prime of t? Well, I can choose by the product rule as a whole. So I get, if the derivative hits the first term, I get a b e to the negative 2 root 2 t plus an a plus bt negative 2 roots of 2 e to the minus 2 root of 2 t. And I want u prime of 0 to be minus 5. So minus 5 equals u prime of 0. U prime of 0, this just becomes a b. This becomes plus a minus 2 square root of 2 from the term at the end. A we already found was 2, and then the b term vanishes again because t is 0. This means that b, if I add this to the other side, is going to be 4 roots of 2 minus 5. And now I can plug a and b into my equation to get my actual solution, which is going to be u of t equals a plus b t e to the minus 2 root 2 t. So there's a couple examples of solving out problems with the stuff you've learned in this section. The big ones here is getting the applications down. So this is the idea of getting from word problems to actual ODEs that you know how to solve. So there's a couple examples there of what that works, and we'll see a bunch more in class tomorrow. All right, so that's it for this video. We'll do more of these in class, and that should hopefully solidify that a little more, how you set these sorts of problems and do things with this. All right, thanks a lot for watching, and I'll see you with the next section.